Project scope and sequence. Choose a location for your pavilion. Site analysis. Design a dynamic public pavilion. Use sustainable materials for the project. Simulate your project using IES. Analyze thermal, wind, and light performance of the pavilion in correspondence to 3 seasonal scenarios: winter, spring, summer, in 3 different hourly changes per day. Compare our results with the region's sustainability assessment method, which is Green Star in our case. Sydney Park, Australia.
Sydney City is the state capital of New South Wales. It is situated in Australia's east coast. We decided to locate our pavilion in Sydney Park, which is located at the western border side of the city. Australia is located in the southern hemisphere. Therefore, summer starts at December to February, winter starts at June to August, and spring starts at September to November.
People can head to the park using public transportation or their own cars. St. Peter's Station is just across the road. Also, you can board buses that travel down Sydney Park Road, Princes Highway, and King Street. Furthermore, there are 4 car parkings around the park. Sydney Park is one of the major parks in the city. It has many landmarks which include cycling center, passive house, historical brick kilns, and tall brick chimneys. It is considered to be a large entertaining area, which contains many amenities such as children's playground, coffee shops, barbecue facilities, public toilets, dog pond, and bike track. Sydney Park is bounded by 2 primary roads and 2 secondary roads.
Climate consultant. We can notice that the highest recorded temperature is 43 degrees and the lowest is 2 degrees. The mean range of the sky coverage annually is 50%. The highest wind speed is 18 meters per second coming from the southwest, and it is below 5% of the hours. Concept development. As a result of the Kiever technique mechanism, we adopted the hierarchy of the glazing strips in our pavilion facade, along with the perforated aluminium louver system with sensor technology, known as pantographic system. In addition, we used solar panels as the roofing to the pavilion to utilize the site's solar energy and convert it to usable energy for lighting. This motivated the main concept in our project, which is the application of a dynamic facade that can adapt to the varying weather conditions. The pavilion framing is made up of steel structure. The elevation consists of 2 layers. The first layer is double glazing on north, west, and east sides. Second outermost layer consists of foldable perforated aluminium louver system with sensor technology to have a kinetic movement that is environmentally responsive to the climate changes of our site, and the upper roof surface is made entirely of solar panels. To comply with Green Star, we chose a material that is recyclable. For the pavilion facade, we selected double glazing with low E value on the inside face to reduce solar heat gain during summer and heat loss through winter to minimize air infiltration. For framing, we used steel grade 450. The dynamic louvers is made up of perforated aluminum with pantographic system. Pavilion dynamic movement of the louvers is motivated by using battery and sensors that sense and adapt accordingly to weather changes. Solar energy. In our solar energy calculation, we compared premium PV system with thin film PV system. As a result, we decided to select premium PV system due to its high efficiency rate of about 12% to 24%. It can withstand the harsh conditions as Sydney experiences hot summers and cold winters. And most importantly, silicon is more environmentally friendly in terms of disposal and recycling time. With our premium PV system, we achieved 6,612 kilowatt-hour per year with savings of $1,983.
IES simulation. This table is showing the daylight hours of the months June, September, and December. Spring season scenarios. To reach to the comfortable level and to get full shading of the pavilion at September 9 a.m., we closed the north and east sides and we opened the west side. This resulted in 5 degrees reduction in air temperature. The highest reduction for the solar gain was in the east room at 67%, caused by opening the pavilion from the west side. At September 12 p.m., we closed the north side and opened the west and east sides. That resulted in 4 degrees reduction in air temperature. The highest reduction of solar gain was in the north room at 65%, caused by opening the pavilion from the east and west sides. While at 3 p.m., we closed the north and west sides and opened east side. That resulted in 4 degrees reduction in air temperature. The highest solar gain reduction is 67% at the west room. Summer season scenarios. In the summer season at December 9 a.m., we closed the east side and opened the north and west sides, which resulted in 4 degrees reduction in air temperature. On December at 9 a.m., the highest reduction was in the east room at 59%, caused by opening the pavilion from the west side. At 12 p.m., we opened all sides of the pavilion to achieve comfortable indoor environment. By comparing base case and model, we got 3 degrees reduction in air temperature. In December at 12 p.m., the lowest percent reduction in comparison with all strategies was experienced in all 3 rooms, east, west, and north, at 41% each. At 3 p.m. in this scenario, we closed the west side and opened east and north sides, which resulted in 3 degrees reduction in air temperature. We can notice that the reduction in air temperature in summer is less than other seasons because Sydney records high summer temperatures. Highest reduction was in the west room at 59%. Winter season scenarios. In winter at 9 a.m., we opened the west side and closed the north and east sides. We reduced 2 degrees in air temperature. Highest reduction was in the east room at 65%. While at 12 p.m., we opened half of the east and west sides and we closed the north. 2 degrees were reduced. Highest reduction was in the north room at 65%. In June, we closed north and west and opened the east. The reduction of air temperature is 2 degrees. The highest reduction at 60. Glare and luminance. In IES simulation, we tested the glare and luminance of our pavilion. September results. After simulating the base case, we can see the glare in the imaginary room. Here we can see the comparison of glare and luminance between the base case and model. Glare is eliminated and luminance range has improved to 150 candela per meter square. December results. This is the base case of the month of December. We can see that the glare is eliminated, but the luminance range improvements are less than September due to the Sydney sunny weather. While in the month of June, both glare and luminance results has improved.
Daylight factor and daylight illuminance. In daylight simulation, we compared the results between the base case and the three imaginary rooms under the pavilion at three different times of the day, which are 9 a.m., 12 p.m., and 3 p.m. in spring, summer, and winter, for both the base case and the model, to see the average daylight illuminance after we put the pavilion to assess daylight and illuminance range. Spring season scenarios. At 9 a.m. in September, it can be seen that after we put the pavilion, the illuminance is reduced to 436.17 lux in comparison to the base case. At 12 p.m. in September, the illuminance is reduced to 698.95 lux, while at 3 p.m. in September, the illuminance is reduced to 434.18 lux. Summer season scenarios. At 9 a.m. in December, the illuminance is reduced to 874.7 lux. At 12 p.m. in December, the illuminance is reduced to 1474.42 lux due to sunny summer season. At 3 p.m. in December, the illuminance is reduced to 861.15 lux. Winter season scenarios. At 9 a.m. in June, the illuminance is reduced to 372.79 lux. At 12 p.m. in June, the illuminance is reduced to 451.30 lux, while at 3 p.m. in June, the illuminance is reduced to 364.53 lux. As a result of the simulation, we can conclude that the illuminance range is between 300 to 1500 lux, which is considered as comfortable range. CFD analysis. We assume the base case to be closed from the four sides. The wind is hitting the surface of base case, which is causing low pressure zone around it. In September and June, we closed the north and west sides and opened the east side. That resulted in low pressure around the pavilion. Wind is hitting the pavilion and it's creating level pressure due to slanted roof. This is the simulation of the second strategy. For the third strategy, more uniformity in pressure levels can be seen. Here we can see the wind flow of the pavilion. It penetrates from the west and exits from the east. Also, internal ventilation of the pavilion has improved. In the fourth strategy, the three sides are open to allow ventilation from all sides and improving indoor air quality. The wind pressure is focused on the west side, and the semi-louvers help to reduce the pressure. In this strategy, the west side is having greater pressure where the louvers opening is dispersing the wind pressure within the pavilion. We can see that the wind pressure is within comfort range throughout the pavilion.
Our sustainability assessment method is a Green Star rating tool. Based on Green Star design and as-built version 1.1 rating, we achieved 3 stars, which is considered to be a good practice. This is the Green Star list of credits and points that we achieved in our project.